Imagine you are developing a new material, maybe a pharmaceutical formulation, a polymer blend, or a battery component. On paper, everything looks perfect. But then comes the real question: what actually happens to this material when temperature starts rising? Does it remain stable? Does it lose moisture silently? Does it decompose earlier than expected? This is where Thermogravimetric Analysis, or TGA, becomes one of the most powerful tools in material characterization. TGA doesn't just measure weight loss. It tells a story of how a material behaves under heat, step by step, revealing its stability, composition, and performance limits. In this video, we'll walk through how TGA works, why it matters, and how professionals use it in real-world material development and quality control. At its core, TGA measures how a material's weight changes as temperature increases under a carefully controlled environment. But here's the key insight many people miss. Every weight change has a reason. A small drop at low temperature often means moisture or solvent loss. A sharp loss at higher temperatures may indicate polymer degradation or binder burnout. And sometimes weight gain occurs, usually signaling oxidation reactions. In a single TGA run, you can uncover thermal stability limits, decomposition temperatures, material purity, presence of fillers, additives, or residual solvents. This is why TGA is considered a foundational technique in thermal analysis. Now, let's look at how TGA actually works inside the instrument. The heart of the system is an ultra-sensitive microbalance, capable of detecting weight changes as small as a few micrograms. As the sample heats, often at a standard rate like 10 degrees Celsius per minute, the balance continuously records mass changes. But precision doesn't stop there. The furnace controls temperature with extreme accuracy, sometimes exceeding 1000 degrees Celsius. A thermocouple ensures the sample temperature is measured, not just the furnace temperature. And the gas delivery system controls the atmosphere: nitrogen for inert studies, air or oxygen for oxidative behavior. In professional labs like Resolve Mass, instruments such as the NETS-SSCH TG-209 Libra ensure these measurements are not just accurate, but repeatable and compliant with global standards. Let's talk about why industries rely on TGA, thermal stability. TGA clearly defines where a material remains stable and where degradation begins. This information is critical for processing temperatures, storage conditions, and safety margins. Moisture detection. Even trace moisture can compromise pharmaceuticals, polymers, and composites. TGA quantifies this moisture precisely, not by assumption, but by actual mass loss. Component identification fillers like carbon black, inorganic residues, or stabilizers leave characteristic signatures. With experience, TGA curves become fingerprints of material composition. Reaction kinetics. By analyzing weight loss rates at different temperatures, scientists can understand degradation mechanisms, not just outcomes. This is where TGA shifts from testing to decision-making intelligence. Now, let's see how this translates into real-world applications. Polymers and plastics. TGA helps determine decomposition temperature, filler loading, residual solvent levels. This is essential for injection molding, extrusion, and long-term durability. Pharmaceuticals. In pharma, TGA is widely used to measure moisture content, study API degradation, predict shelf life. A small weight loss curve can mean the difference between product approval and failure. Composites and ceramics. TGA tracks binder burnout, calcination behavior, and filler stability, critical for sintering processes. Metals, energy, and environment. From oxidation studies to battery materials and waste characterization, TGA supports process optimization and sustainability goals. Here's where TGA becomes even more powerful. On its own, TGA tells you when mass changes. But when combined with other techniques, it tells you what is actually happening chemically. TGA-DSC simultaneously measures mass change and heat flow, helping distinguish melting from decomposition. TGA-FTIR identifies functional groups in evolved gases, perfect for polymer degradation studies. TGA-MS provides molecular weight and composition of volatile products. TGA-GC separates and analyzes complex evolved gas mixtures. In advanced material development, these hyphenated techniques are often the difference between assumptions and certainty. Professional TGA isn't just about running samples, it's about controlled execution and expert interpretation. At Resolve Mass, the process begins with careful sample preparation, aligned with international standards. Next comes precise temperature programming, often extending beyond 1000 degrees Celsius. The atmosphere is selected intentionally, inert, oxidative, or vacuum, depending on the study objective. Finally, the most critical step, data interpretation by experienced scientists. Because a TGA curve without expertise is just a graph, with expertise, it becomes a strategic tool for product development. TGA data directly influences material selection, regulatory submissions, process, optimization, product safety. That's why professional services matter. With skilled thermal analysis, specialists, high-resolution instrumentation, ISO-compliant practices, clear, actionable reports. You move from raw data to confident decisions. If you're working with materials where performance, stability, and reliability matter, partnering with experts ensures your results stand up, scientifically and commercially. Thermogravimetric analysis isn't just a test. It's a conversation between heat and material, revealing truths that other techniques simply can't. And when interpreted correctly, TGA becomes one of the most valuable tools in your material characterization toolkit.